Okay, so hopefully we don't have same connectivity issues that we had yesterday. So finishing up what got cut off from the end of yesterday's lecture. So we had done this example um, of showing that 6 was a primitive root mod 41. And so the way that we did this, of course, was if we let m be the order 6 mod 41, then we knew that in this order has to divide 40 by the order theorem, and so you can just list out the divisors of 40. But once you do that, if you judiciously pick which of these you're actually going to compute, so we chose 20, knowing with some foresight that this was going to rule out divisors of 20. So it was if we could rule out 20 as the order, then this meant that it ruled out any divisor of 20. So it ruled out 10, 5, 4, 2, and 1. So checking 20 was a smart choice here, and it turns out, yeah, so 20, and we just have to do this computation using, the modular exponentiation algorithm. But once you do that and you see that it's congruent to -1 mod 41, then you know that m can't be 20. But if it can't be 20, then it can't be any divisor of 20. So just to show that if m was 5, right, 6 to the 5 would be congruent to 1 mod 41. But then 6 to the 20 would be 1 mod 41, but it's not. It's -1. So we know that 5 can't be. Similarly, we know that 10, 4, 2, and 1 can't be. So when you rule out 20, you rule out all of those. So then the only other thing you have to check, you're left between 8 and 40 is the only thing left. So you just check 8 again by brute force and see that it's not. It's congruent to 10 mod 41. So then the only other option left is 40. And since 40 is 41 minus 1, then 6 is a primitive root mod 41. And so basically, what happens in this example is not specific to these numbers in question. This actually gives a quick way of going through this, and so that way is listed here. So let P be prime, H not be congruent to 0 mod P. Then the following are equivalent. So H is a primitive root for P. That is the thing that we want, but the actual thing that we're going to use to check whether H is a primitive root for P is this next criterion, which is for each prime L dividing P minus 1, H to the P minus 1 over L is not congruent to 1 mod P. Okay, so this is essentially what it is that we did in this process up here. Okay, so this just gives a nice, efficient way of dealing with this. Another thing that this tells you right off the bat is that this allows you to find primitive roots, pretty quickly. But you have to know the factorization of p minus 1. So note, if we know the factorization of p minus 1, then this method is pretty quick. Okay. All right. But if you can't factor p minus 1, then verifying whether or not a number is a primitive root mod some prime is trickier. That would be harder. This certainly doesn't give you a method for doing that. But in the event that you know the factorization of p minus 1, this gives you a pretty quick way of doing it. And essentially, like I said, we're using the same process we used in this example here. Okay, and so the thing that I was talking about at the very end of yesterday's lecture before I got cut off um, is the following. So this is the question. What if I start with an integer and then ask for what primes is this integer a primitive root? I.e., here's an example. Let h equal 2. Then h is a primitive root for the primes 3, 5, 11, 13, 19, and so on. We could keep going here. Um, so it turns out it is a primitive root for 67 of the 168 primes less than 1,000. Okay. Okay. So I could continue that list quite a bit. Naturally, first question is 2 a primitive root for infinitely many primes? And it turns out that questions like these are very hard. Um, they are very hard. And the reason they're very hard, well, I'll maybe I should say that really, I guess the thing that should give some motivation. This isn't the reason they're hard, but this is something that gives some motivation as to why you might imagine something like this is a tough question. Um, is that there is a relationship between a more generalized form of the Riemann hypothesis. It's called the generalized Riemann hypothesis, which has not been proven. But the questions, I'm well, I might state the general. It's called Artin's conjecture, but uh, the more general sorts of statements, like the question is to primitive root for infinitely many primes. This is so the only proofs that exist of this assume the generalized Riemann hypothesis, which itself has not been proven. So I believe the best result that doesn't rely on any assumptions uh, was proven in the mid 80s. And it's that there's at most 2 primes that are not primitive roots for infinitely many primes. Um, so, for instance, the example that's given in the book is consider the list of 3 primes: 2, 3, and 5. By that result, at least one of those is a primitive root for infinitely many primes, but you can't say which one. So, this is open. Um, so, uh, a more general statement has to do with the following. Um, this I'm not gonna like formally state it, but basically this is uh, um, the idea is that under some assumptions, I think that h can't be a square or negative a square. I think is what it says. Then so h not a square or minus a square, then h is a primitive root for infinitely many primes. Okay. And in fact, there was a specific ratio. Um, Basically, there is a positive, h is a primitive root for a positive proportion of primes. So there is a ratio c sub h that is this limit as x goes to infinity of the number of primes p such that p less than or equal to x is prime and h is a primitive root for p. So this is the set of primes p less than or equal to x for which h is a primitive root for p, divided by the total number of primes less than or equal to x. Okay. So in fact, the existence of this constant was conjectured as part of this, and the conjecture, or maybe even subconjecture, is that for h equals 2, this is supposedly, so c sub 2 is approximately 0.37395558 and so on. You can compare this with the proportion that I gave above here, that 67 of the 168 primes less than 1000, 2 turns out to be a primitive root for. Okay. So this is with no assumptions. This is still open as far as I know, and with it has been proven with the assumption of the generalized Riemann hypothesis, which itself, of course, is not proven. So that's a neat fact, but under no extra assumptions, this hasn't been proven. And as I said, I think the best result is that there are at most 2 primes that are not primitive roots for infinitely many primes. And so, like I said, while it's not known if 2 is a primitive root for infinitely many primes, if you consider 2, 5, and 17, then it's known that at least 1 from that list is a primitive root for infinitely many primes. Okay. So yeah, this converse question, this backwards question of starting with an integer and asking for what primes it's a primitive root of, that's a much harder question. Okay. So I wanted to quickly talk about decimals, and a lot of what we're talking about here, of course, could be done in other number bases, but we're going to use base 10. So we're going to talk about decimals. Now, before we get into talking about decimals, I'm going to talk about a story that's completely unrelated to, well, it's not entirely unrelated, but it doesn't show up in the textbook, and it doesn't show up anywhere online because this is something that happened to me. So first, a story about decimals. So when I was an undergrad, I worked in the math tutorial center at the University of Tennessee. So it's very similar to how, well, I guess it's not that similar to how the tutoring room works at UMD, but I don't know about all the other various like math tutoring options on campus. So there might be some tutorial center somewhere on UMD's campus that functions similarly. But anyway, so the one at UT was it was this big complex of rooms in a part of the math building, and so me and a bunch of my friends worked there a few hours out of the week or something. And anyway, I had one of my friends comes in, and he is like scratching his head. He's really confused because he's just come from talking with a student, helping a student through this worksheet that the student was doing, and he was completely baffled by how the student was doing math. So the student was doing some very, very basic. I guess this was some like remedial like college algebra type stuff And the worksheet in question was, this is near the beginning of the semester, so it's kind of like a foundational worksheet, and it was literally a worksheet for converting fractions to decimals. Okay. And so my friend had been helping the student, and the student's answers on the questions for converting decimals and fractions were just completely all over the place, and they didn't make any sense at all. So the student explained that, in the one time in their like academic career when they had seen, when they were supposed to have seen this conversion take place back in, I don't know, third grade, fourth grade, whatever. They had like moved schools or something, and like there was a gap of a few months of their math education. They had never actually seen how to do this. Whatever, for whatever reason, doesn't really matter. The point is that they were having issues converting between fractions and decimals, and so for instance, they were taking, say, the fraction 13 over 7. Well, I mean, clearly this is 7.13, right? So clearly that's exactly what that fraction is equal to. Well, not really, right? So, of course, what about, because this was one of the examples that showed up on the worksheet in question. What about 6 over 6, right? Well, we know that one. That's 1. Okay, but actually 6 over 6 is 6.6. Right? No. Okay. So then once it became clear what the student was doing, so obviously like 10 over 3 is most certainly 3.1. Right? Oh no, wait. That's no good either. Right? So, you might look at this and say, why would anyone ever think to do this? And that's exactly what he asked the student. And the student said, oh, well, very clearly this works because 5 over 2 is 2.5. Right? And hey, like that works, right? That works. So I saw this and I thought this was amazing when my friend was relaying this to me. And when, I considered the fact that, yeah, this works in this case. So, the student is clearly doing some, if you have y over x here, these are positive integers, we'll say, then this is clearly x point y, where we have just stuck, I could write this out in base 10 if I wanted to, and in fact we're going to do exactly that sort of thing here in a second. So I could write this out in base 10, but obviously when I say x point y here, what I mean is that I took the digits in y and stuck them behind the decimal, right, in that order. So again, you can, this is my notation for it, but you understand what's going on there. So this was the student's claim, of course, that when you had a fraction y over x, well, that's just the decimal x point y. That totally makes sense. And of course, the reasoning is that it works in this case, right? 5 over 2 is indeed 2.5. Okay, well, my immediate response was, I bet that is the only, this is the only pair of integers this works for. And so then I got kind of interested to check, and so I tried to check, when is this true? So for what x and y is this true? So I tried to prove that this was the only time it worked, and I wasn't I wasn't successful at doing that, but I showed some restrictions that had to occur between these two things. Of course, if you think about it for a second, if you write this in a better form, then there are some restrictions placed that massively limits the x and y that are viable pairs here. And so using that, and some friends of mine who also became interested, and with the help of some computers, I think we checked up to like 20 something digits, and up to 20 something digits, 2 and 5 are the only ones that work for this. I haven't thought about this in like 13 years, but that was the state of it back then. I think we also, though, we found an infinite sequence of integers for which you could make these two quantities arbitrarily close to one another, but they weren't equal. So you could get them really, really close. And like I said, there was a sequence of pairs that did this. But 2 and 5 were up to many, many digits were the only things this worked for. We also formulated some similar stuff in other number bases. But anyway, so that was, I haven't thought about this in many years, so it's possible that there's a quick elementary way of proving that 2 and 5 are the only ones that this works for. But we will tentatively call this an open question. But this is unrelated to where we're heading in the class, but it's a funny example of how number theory is neat, because some really stupid thing like this can lead to some questions that are I don't know, maybe you don't think this is that interesting, but I thought it was pretty funny. Another one that was a random thing that I gave a Calc 3 exam a few semesters ago, and when I gave on the Calc 3 exam, I think it was on the change of variables integral, I gave them a constant that actually made everything work out nicely, but they had to notice that, so the constant I gave them was 343, but they had to notice that was 7 cubed. So then you have obviously 343 is 7 cubed, but that's 343, right? That's it's kind of neat, right? So I asked my TAs like if they could think of other numbers that had something, and I didn't put any restrictions on like how, I didn't say 3-digit numbers or whatever, so the numbers could be any length, and this length of, I left it up to them to decide, like, would it be like the first 2 digits raised to the last however many digits, or would it be all the digits raised to the last digit, like however they wanted. I told them, come up with this, and it was funny to see them struggling to think about this. They became immediately interested, even though none of them, I think, was into number theory at all. So anyway, okay, all right. So decimals. So rather than actually write out this long division, I'm going to refer to the book here. So the book lists the powers of 10 mod 7, right? So 10 to the first mod 7 is 3, 10 squared is 2, 10 cubed is 6, 10 to the fourth is 4, 10 to the fifth is 5, and 10 to the sixth is 1, right? And of course 10 to the 7th is just going to repeat after that once you have 10 to the 6 is 1. So then let's just look at the long division calculation of 1 over 7, right? So divide 1 by 7, okay, and if we remember how to do this from elementary school, right, we do this we're using the standard algorithm here, no weird alternative algorithms. So we have 1, 0, and 7 here. The remainder is 3. A 0 comes down, so that's 30. Next remainder is 2, so that becomes a 20, and I keep doing this long division process until I get remainder 1. But notice exactly what's happening here, right? At each step, these remainders, of course, are just the powers of 10 mod 7. So the first remainder is 3. There it is. The second remainder is 2. That's 10 squared mod 7. The next remainder is 6, which is 10 cubed mod 7, and so on, right? So there we go, all the way to 1. And of course, this is a repeating decimal, right? So this just repeats. Once you get to this, you drop the 0, and now you have a 10 minus 7, which gives a remainder 3 next, which is 10 to the 7, is 3 mod 7. Okay. And so that's exactly how that process works. But you get, again, that 1 over 7 in decimal form from this is 0.142857, 142857, 142857, and so on, right? It just repeats in this fashion. Okay. So, what we say about a decimal like this is the block that repeats, right? And so if I know this block, there's a more convenient way of writing this decimal. It's 142857 with a bar over top of it to signify that it is repeating, right, infinitely after this decimal place. Okay. So this this block. The length of this block is called the period length, right? Okay. Or just the period, sometimes it will be called. So this is the period length. Now you might already notice what it is that determines the period length, right? In fact, going back here, y, if I look at the powers of 10 mod 7, y is the period length in this case 6, right? So period length here was 6. Why might the period length for that decimal expansion be 6? Well, because the order of 10 mod 7 is 6. Okay. So that's why. It's because when you list out the powers of 10 mod 7, you get 6 distinct entries, right? Okay. Non-zero entries, anyway, I should say. Okay, so what does this mean? Of course, we already have other examples. 1/3 is just 0.3 repeating, which I can now write like this. This has period length 1. Okay. So the block of digits that repeats after some point is length 1. It's just a single digit that repeats over and over again. Okay. So, definition. A decimal for which the repetition begins immediately after the decimal point is called purely periodic. While in general, these are called periodic. Okay, so these are called periodic decimal expansions. Okay. Now, I've said a decimal for which the repetition begins immediately after decimal point is called purely periodic. So both of these, that's true for. The repetition block begins immediately after the decimal. So these are both purely periodic, right? So decimal expansions. for 1/3 and 1/7 are purely periodic, just as an example. Okay. All right. Now, why am I talking about this now after the stuff that I've been doing the last couple sections? So one, you'll see how I've already mentioned how this relates to order. So indeed, that's going to be front and center in this discussion of decimals. But also, this last question we talked about with Artin's conjecture and all that. So Gauss in the 1700s, I believe, asked whether there's infinitely many primes p where the decimal expansion of 1 over p has period p minus 1. Okay, so some motivation. So Gauss asked, is there infinitely many primes p where the decimal expansion of 1 over p has period p minus 1. Okay. Okay. But turns out, and we'll see that after I talk about this next proposition. So it turns out that this is the same question as the following. Is 10 a primitive root for infinitely many primes? Okay. And so this original question asked by Gauss, phrased in terms of decimal expansions of some given fraction, 1 over p, having a certain period, that is actually related to this earlier question we asked about some given integer having or being a primitive root for infinitely many primes. Okay. Okay. So now, to see what links these sorts of things, here's a proposition. So let m be an integer bigger than or equal to 3. Let it satisfy GCD of m and 10 is 1. Okay. And let b be between 0 and m strictly with b and m relatively prime. Okay. Then the period length for the decimal expansion of the fraction b over m is the order of 10 mod m. Okay. Therefore, the period length for the decimal expansion of b over m divides phi of m. Okay. That last sentence, of course, is once you know that it's the order, then that last sentence is just the corollary of the order theorem. So that's not. Um, so that's not too much. If we can show this first bit, then we're good. Okay. All right. So think about what this is saying. This allows you to compute the period length for decimal expansion of any fraction like this b over m in terms of the order of 10 mod m. Okay. And why? You'll notice that there's going to be all these requirements that we have for all these theorems that we're going to state. That the integer that we deal with, of course, doesn't have any common divisors, or certainly doesn't divide the base 10 itself. It's for this reason that you'll hear a lot of people say sometimes that perhaps it would be better to use a prime base for your number system for a number of reasons. There's a number of reasons why using a prime base would be preferable, right? Maybe we should use base 11 instead of 10 or something. So anyway, so how do I prove this? So this is the only proposition involving the decimal stuff that I'll prove the next one too, just because it's important, but then I'll leave, when we talk about Mitey's theorem, I'm going to leave the proof of that to you. So how do we prove this? Well, first, an example. So here's an example. Let's say you have 3 over 11. Okay, so 3 over 11, its decimal expansion is 0.27, 27, 27, 27, and so on. Okay. All right, but there's a way to rewrite this that allows us to make use of the fact that we know how to sum a geometric series. So another way to rewrite this, of course, is 27 over 10 squared. That gives me 0.27 and then a bunch of zeros. So I need the next block of 27s. So that's 27 over 10 to the 4th will get me this second block of 27. And then the third block of 27 comes from 27 over 10 to the 6th. Right? Okay. And of course, I can continue doing that. Since this repeats indefinitely, this is an infinite sum. But it's an infinite sum that I can use geometric series stuff to do, right? So what is this? Right? If I actually try to write this as if I were to try to sum this, what do I get here? Well, I mean, I get, if I'm thinking about what it is that I'm doing here, this is 10 squared is the thing that is being, or sorry, 10 to the minus 2 is the thing that's being raised to the power, in here in my geometric series, right? And so what do I get? So I get using the geometric sum formula, I get 27 over 10 squared over 1 minus 10 to the minus 2, right? Which is 27 over 10 squared minus 1. No. Okay. Now, you might look at this and say, wait, this is like a really dumb way of writing this fraction. We already have it written as 3 over 11 here, so what is the purpose of writing it in this way? Okay. So we're going to see what the deal is. So in this particular example, right, we know that it's 3 over 11 like this. But the thing is that we actually, we want to put it in this form because it's going to allow us to easily see that this period length is the order. Okay. So I'm just using, this uses the geometric sum formula. Okay. So now I want to continue the proof using this fact. So that example is the thing that motivates me to do it this way. So proof of this fact. Well, so any periodic decimal expansion can be written in the same form as the previous example. Okay. So say it repeats every n terms, right? So say it repeats every n terms. Then we can write it as following: a over 10 to the n plus a over 10 to the 2n plus a over 10 to the 3n, and so on. Okay. But going back to my example to show what it is that's going on here, for 3 over 11, we saw that it repeated each block of 2, so it was 0.27272727 on and on. That's what made us write this first thing of, well, this is 27 over 100, which is 10 squared, plus 27 over 10,000, which is 10 to the 4th, plus 27 over a million, so which is 10 to the 6th, and so on, right? So this is how we wrote it like this. We didn't even necessarily directly think that, oh, it repeats every 2 blocks, so I'm going to do this thing. I just looked at the decimal itself and wrote it like this, right? But the point is that we could do that. Imagine that this decimal repeated every 3 blocks instead. Well, then we could do exactly that sort of thing. Instead, we would have whatever those 3 digits are over 10 cubed, whatever those 3 digits are over 10 to the 6th, 10 to the 9th, and so on, right? We would have that block over increasing powers of 10 like this. So this is what's going on here. So if it repeats every n terms, this is the form that it takes. And so now using the geometric sum formula, again, this is a over 10 to the n over 1 minus 10 to the minus n. Okay, which is, once we simplify that, that is a over 10 to the n minus 1. Okay. All right. So, for sum a, right? For sum a. So, if b over m repeats every n terms, then b over m is equal to a over 10 to the n minus 1 for sum a. Okay. i.e., multiplying, right, cross multiplying here, 10 to the n minus 1 times b is equal to big A times m, i.e. m divides 10 to the n minus 1 times b. you see where I'm going with this. But the GCD, I should say GCD of m and b is assumed to be 1. So if m divides this product, it actually has to divide 10 to the n minus 1. Okay, i.e. 10 to the n is congruent to 1 mod m. Okay. All right. So we are not quite done yet, because we've said that we have a fraction b over m that repeats every n terms. Right, so that's its period length. And then we've shown that this 10 to that period length is congruent to 1 mod m. Right? So we want to show that it is the order of 10 mod m. So we're going to do that, but before we show that this is the smallest n for which this works, I'm going to start with another statement, which says, conversely, let's just assume, so if 10 to the n is congruent to 1 mod m, then 10 to the n minus 1 is equal to little a times m for some a. Right. And since b is strictly between m and 0, ab is strictly between am and 0, but am is 10 to the n minus 1. And furthermore, b over m is the same thing as ab over am. Right. Which is the same thing as a times b over am is 10 to the n minus 1. But using the geometric sum formula in reverse, this is ab over 10 to the n plus ab over 10 to the 2n plus ab over 10 to the 3n, and so on. So it repeats every n terms, right? So what have we done so far? All right, so to polish off our proof, so we have shown that b over m repeats every n terms if and only if 10 to the n is congruent to 1 mod m. All right, so what's the last thing we have to say? Well, the smallest such n, right, the smallest such positive n is the period of b over m, and is simultaneously the order of 10 mod m. So that's it. Or I should say the last statement, or the last sentence in the prop, is by the corollary of the order theorem. Okay, so what is the only thing that could have gone wrong up to this step? Basically, it's that the block of n that you chose was a huge block, right? So for instance, when you look at this decimal, What if you didn't notice that it repeated after 2 terms and you said, oh, it repeats after 6 terms, right? Well, that's true. I mean, it's those 6 terms and then it's those 6 digits, then the next 6 digits, and the next 6 digits. That's true, but that's not the period length, because the period length is the smallest such block, right? I wasn't that clear about that earlier when I mentioned it. So the period length is the smallest such block for which this thing repeats. Okay. So once you see that, of course, what this means is that we could have chosen a block stupidly like that, right? But of course, if we just pick the smallest such one, you can see automatically how the smallest such one is going to be the period of B over M, since it's defined that way. And it's simultaneously the smallest such n, such that this is the case, is the order of 10 mod M. So that does it. Okay. So, of course, here's some nice examples of this fact. So 1 over 7 is, of course, 0.142857 repeating. This has period length 6, right? And the order of 10 mod 7 is 6. 1 over 11 is 0.09 repeating. This has period length 2. And the order of 10 mod 11 is 2. Okay. So then 1 over 13 is 0.076923 repeating. And this has period length 6. And notice that the order of 10 mod 13 is 6. Okay, and lastly, 5 over 21 is 0.238095 repeating. And this has period 6. And the order of 10 mod 21 is also 6. Okay. Now, all of these are examples of numbers that are purely periodic, right? If you recall our definition, purely periodic means that the decimals repeat immediately following the decimal sign. Okay. So, of course, you know that that is not what a general decimal expansion looks like. So, what if we have a number that's like 0.123 and then it repeats? Right? Or even something like 0.123 and then it's just nothing but 0 after that, right? It also counts. These are called eventually periodic. Okay, which has an obvious sort of definition, which is just that eventually they repeat, right? So eventually there is this repetition, and so past a certain point we could stick a bar over some block that the smallest block we could do that for is the period length, and then it just repeats after that. Of course, there's a more elegant way you could, well, I don't know if it's more elegant, but it's a more formal way that you could say that in terms of, well, we're about to see in the proof of the next theorem, like how you could explicitly state eventually periodic in a precise way. So now that I've said this, of course, there's immediately a question surrounding something you've probably heard before, a characterization of irrational numbers, which is the true statement that if a number is irrational, right? So if you have a real number and it's irrational, then it must have a decimal expansion that is infinite, and that is, when you say infinite, meaning infinitely non-trivial. There's not some string of infinite zeros at the end of it. Okay, so it's non-zero, digits. Not all 0 digits populate its last infinitely many digits in its decimal expansion, and it can't be eventually periodic, right? So it can never eventually start repeating. Okay. So looking at the contrapositive of that statement I just said in terms of irrational numbers, that means that a number is rational if and only if its decimal expansion is eventually periodic. So theorem. Okay. A decimal expansion of a real number x, and for us, we can call real numbers the numbers that have decimal expansions. So a decimal expansion of a real number x is, I don't know why I put a comma there, is eventually periodic if and only if x is rational. So the rational numbers are exactly the ones that have decimal expansions that are eventually periodic. So proving such a statement might have been confusing to you before you had seen kind of an example of how proofs involving decimal digits work. But the way that this goes is the following. So if x has a decimal expansion that is periodic, or decimal expansion that is eventually periodic, then x is periodic, say past some kth term after the decimal point. Okay. But then 10 to the k minus 1 times x is an integer plus a purely periodic decimal. So here is the characterization of eventually periodic that I said, was more precise, which is, if it's eventually periodic, the nice intuitive explanation is it repeats after, like, eventually, some point after the decimal place is where the repetition starts, not immediately after. Well, then, abusing the fact that it's base 10, right? You multiply by copies of 10. Of course, if it starts repeating after the kth term, you multiply by k minus 1 copies of 10. And that just shifts the decimal point, right? It shifts the decimal point right all the way till the point it starts repeating, right? And so now it's just an integer. That's everything to the left of the decimal. And behind the decimal, you have the part that repeats. So it's a purely periodic decimal, right? Okay, so then the purely periodic decimal, you can use the formulas for geometric sum just as before, right? So then this purely periodic, what am I doing? Decimal can be evaluated using the formula, can be evaluated using the formula for geometric series. Okay. And of course, the formula for a geometric series is integer divided by integer. So this gives a rational number. Okay. Since 10 to the k minus 1 times x is minus an integer, is an integer, then so is x. Or sorry, 10 to the k minus x minus an integer is not an integer, it is rational. Then so is x. Okay. So this is actually a constructive proof because, and you might have seen this before if you ever, if you ever did any of these things forever ago in school where you converted, stranger decimals into fractions or vice versa. So this is actually going to tell us how to do it in both directions. So it's constructive proof in both directions. So to see an example of how you do this, say that you start with the number 150, say 154.74123.123.123, and so on after that. Okay. So if you wanted to convert this to be, if you wanted to show that this was rational, what would you do here? So the idea is that you take this thing and you say, okay, this is an eventually periodic decimal expansion that starts repeating here, right, at the third place after the decimal. So I need to multiply this by 10 squared to move the decimal over here. So I do that. So I multiply by 10 squared. Okay. So multiplying by 10 squared here, I get 15,274. Now 0.123123, and so on. So now it's purely periodic. Okay. So then I can split this, right? So maybe I say split this in the following way. I could say that this is 15,274 plus the decimal 0.123.123.123 plus whatever else is needed, right, to get the rest of it, right? So this is where I use the geometric sum formula. So this is 15,274 plus this would be, according to how my geometric sum works, this would be 123 over 10 cubed minus 1. So this is 15,274 plus 123 over 999 would get that done. Okay. So then once you've done that, you could say, wait, but you started out by multiplying by 10 squared. So then what do you do? Well, okay, now just divide by 10 squared. Divide by 10 squared, then you have rational plus rational, so it's rational, right? So this is how it is done, okay? This is a nice example. It shows you how this constructive approach works. And so this actually gives you the process for converting a decimal expansion that's eventually periodic to a rational number, okay? So that is the forward direction. So let's do the backward direction. So backward direction. If x is rational, then for some k sufficiently large, ten to the k times x can be written as t plus r over s, where t is an integer and r is, that numerator is strictly between 0 and s, and GCD of s and 10 is 1. Let's think for a second why we can do this. So if x is rational, so it is some fraction, okay, then why do I know that for k potentially huge, 10 to the k times x eventually can be written as integer plus this fraction r over s, where the numerator is smaller than the denominator and denominator is relatively prime to 10. Why do I know that? Well, I know the prime factorization of 10. Prime factorization of 10 is just 2 times 5. So by multiplying by powers of 10, I can clear out all copies of 2 and 5 in the denominator of x, right? And so eventually I will clear out all of those, and this will be the expression that I'm left with, right? I'll be able to write this as integer plus a fraction r over s in this way, okay? So I just multiply by as many copies of 10 as I need to clear all those 2's and 5's from the denominator, okay? But then r over s has a purely periodic decimal expansion. Okay. Period is the order of 10 mod s. Okay. Then adding t and dividing by 10 to the k yields a decimal expansion. That is eventually periodic. All right. So 10 to the kx looks like this, and then I can, once I have that this can be written in this form, well, then x itself is going to have the eventually periodic expansion just by taking this thing and dividing by 10 to the k, right? Okay, that's going to give it to me. Okay, so that's it. And again, this actually gives you the process for converting between decimal expansions and fractions in this way. Of course, what is required is that these things be eventually periodic, right? And if they're not, there is no conversion process because, well, those things are irrational. So of course there's no conversion process. Okay, so one more thing about decimals that's neat, and then we'll move on to the next topic, which I probably don't know if I'll have a chance to start on today, but if not, then I'll start and finish it tomorrow. Okay, so Mighty's theorem, and I just wanted to do this so that I didn't have to go through the hassle of rewriting all this stuff. Let me make sure that this is not, I'm going to have to there we go. Okay. So, Mighty's theorem, before I state Mighty's theorem, I just want you to notice this neat thing. So I have two decimal expansions, so 3 over 17 and 8 over 13. So here are their decimal expansions. You'll notice that both of them are periodic, but they have pretty long periods. So for instance, in 3 over 17, the period or the block is 176470588235294 and then it restarts at the 176 block here. Okay. All right. So that's a length 16 block. Okay. So the first expansion has that as its period. That has length 16. So split this in half. Okay, so split it in half. Since it's length 16, I can split it into 8 and 8. And if I split it and then add the two halves, meaning I split it in this way and then literally just take the two numbers that result and add them as integers, right, in base 10 addition, then what do I get? So then this 8, this second 8 gets added to 1. That's a 9. 7 plus 2 is 9. 6 plus 3 is 9. 4 plus 5 is 9. 7 plus 2 is 9. You get nothing but 9s here. So that's interesting. All right, but what about this other decimal? So this thing has period 615384. So that's period length 6. So take the 615 and the 384, split those and add them. So 615 plus 384, again, you get 999. Okay. So this was, this pattern was noticed in the early 1800s. And this pattern is called Meidy's theorem, or maybe Meady's theorem. I can't remember. I think it says he's French, but here, I'm going to have to refocus my camera. Oh, there we go. Yes, okay. So this is Meidy's theorem. So let P not be equal to 2 or 5, but let it be prime. Okay, so it's a prime that's not 2 or 5. Probably doesn't take too much imagination to imagine why you don't want 2 and 5 here. But that's a good thing to ask. I'm not saying that that's necessarily totally obvious, but you should think in terms of what we're doing, why 2 and 5 might be no good. Okay. And let A be an integer between 0 and P strictly. And let A over P have decimal expansion. It's purely periodic. So we'll call the digits C sub 1, C sub 2, C sub 3, and so on, all the way to C sub m. And it's purely periodic, so that block repeats, right? So let this be the decimal expansion of A over P, where m is the period. Okay. So m is the period, so it's not this block isn't inefficient. This is exactly what m is. Okay. So then suppose m is even. Well, in order to be able to split this in half, it needs to be even, right? i.e. m is equal to 2n. Okay. Then added as integers, c sub 1, c sub 1, c sub 2, c sub 3. This is the integer formed with these digits plus c sub n plus 1, c sub n plus 2, all the way up to c sub 2n is equal to 9, 9, and so on, 9, where there are n nines. Note, this is addition of integers in base 10. Meaning those digits are the digits of integers in base 10. So, i.e., C1, C2, C3, all the way out to Cn represents the base 10 expansion. C sub 1 times 10 to the n minus 1 plus C sub 2 times 10 to the n minus 2, and so on all the way down to the constant term C sub n there, right? Okay, so I'm not going to go through the proof of this. It's actually, once you've seen the proof of that proposition we proved earlier today, this is more of the same kind of algebra that's done here. So this is on page 254. So this is the statement of Mitey's theorem. It's pretty funny that I mean the way that this works is kind of neat. There's versions of Mitey's theorem not just for base 10, and I should say that when you're talking about properties of decimal expansions and stuff, a lot of the stuff you want to say, of course, carries over to other number bases, and you might even see exactly how that works already just from the role that 10 plays in these proofs. So if you replace 10 with b for a generic number base, then you might already see, as I said, how this works. So anyway, so this is kind of a neat little pattern that occurs. As I said, here's these examples I listed before are pretty nice, and of course this always works. So you are welcome to try to do that. With any, so cook up a decimal having whatever period, as long as you have an even period length, right? So cook up a decimal that arises in this fashion and just show that this works for that particular example. It's pretty neat. So anyway, I think that's all I'll say today. I could state the discrete log problem in like a minute, but I'm going to wait and do that tomorrow, since the two crypto applications I do that go with it both rely on discrete log problems. So I'll save that till tomorrow. So tomorrow we are going to do 11.5 and all of chapter 12, which is only 2 sections of chapter 12. And then maybe by the end of tomorrow we'll start on chapter 13, but if not, then we'll do it on Thursday, starting on chapter 13, which is quadratic reciprocity and is like probably the most important part of this course. So by later today, I'm going to reorganize the lectures and put them. I'd only put like the first 2 weeks on the syllabus page, so I'll put all of them on the syllabus page and update and make sure that all of the YouTube descriptions match everything. Because sometimes the YouTube descriptions include something that we didn't quite cover in that lecture, so I don't want you looking through a lecture and trying to look for something that wasn't covered. So I'll update all those by this evening. That way, if you're looking through these lectures, the description will be completely exhaustive and won't tell you that something's there that's not. Okay. So anyway, I will see you all tomorrow.